Good afternoon, everyone, on site and online. It's my pleasure to welcome today Sergey Khoperskov, visiting Heidelberg. Sergey is currently a postdoc at the Leibniz Institute for Astronomy in Potsdam, working with Minchev, Steinmetz, and others on some numerical simulation, galactic archaeology, chemodynamics, using abundances, stellar ages, and Gaia as well. Sergey has been in the galactic archaeology community for a while now. He defended his PhD back in 2013 at the Institute of Astronomy of the Russian Academy of Science, where he got the prize of the best thesis. Then he moved to Milano to work with Giuseppe Bertin, and then moved to another postdoc to Paris Observatory, working with Misha Wood and Paola Di Matteo mainly. And at the same time, he was a regular visitor in Heidelberg at HARI. And his last postdoc before arriving in Potsdam was in Garching, MPE, where he worked with Ortwin Gerhard. So the floor is yours, and then we're going to have some questions.
Hello, everyone. Hope you can hear me well. Thanks a lot for the kind invitation to present my work. And it's always nice to be back in Heidelberg, especially during summertime, which we don't really enjoy much in Berlin, to be honest. Today, I'm going to be talking about Milky Way galaxy, and together with you, we're going to rediscover it, but rediscover in a good way. If you think that for some reasons my laptop fell asleep and you're watching classic Microsoft screensaver, it is not correct. We're currently flying through the Milky Way, and each point here is a real star in our galaxy. So actually, we're just moving through the galactic center, and we're kind of obviously I'm not showing you all the stars. Otherwise, that would be too bright. But now, since we reached the farther side of the galaxy, we're turning back. Now we're gonna see our galaxy, the Milky Way. You see that since we turning around, the density number of stars we can see increases, and everything becomes essentially white. So stars are everywhere. And still, even in this case, obviously, that's not all the stars we have in a galaxy, not all the stars we have a chance to observe. Okay, so that would be the topic of today's presentation. And the official sponsor of our journey is, of course, the European Space Mission Gaia, which was launched about 11 years ago, right? And it's successfully working, delivering lots of information. So nowadays, it's a holy grail of, well, essentially almost all galactic studies. So let's say in the context of galactic archaeology, maybe the most important deliverable from Gaia survey is this line. So you can see that the number of stars actually measured, the number of stars with measured parameters by Gaia, it's almost 2 billion. It's still a tiny fraction of all the stars we have, but still it's crazy huge number. But for, let's say, galactic archaeology, galactic studies, we want to not only observe the galaxy, how it is, but also just to understand how the things are moving around. So that's why, let's say, the starting point for galactic archaeology, again, is the, let's say, number of stars, number of targets with precise radial velocities measured by Gaia. So currently, we have about 33 million stars with so-called full 6D phase-space information, where we know 3D positions and 3D velocities of stars. If we combine this phase-space information with data from different spectroscopic surveys like GALAH, APOGEE, LAMOS, Gaia-ESO, and many others, we can start adding more information, or if you want, more dimensions to our data set. So obviously, the main goal of Gaia as a survey and many other that I mentioned already is to understand the present-day structure and the history and formation history of our galaxy. And that's what I'm going actually to talk about, starting with a very short introduction, just brief reminder what the Milky Way galaxy is. So fortunately or not, the Milky Way is a typical disk galaxy, the bars, spiral arms, so nothing special, maybe apart from the fact that we are living here, right? But at the same time, the fact that our galaxy is not special makes the study of the Milky Way, understanding physical principles, physical processes governing its evolution, allow us also to use this knowledge to understand how many other galaxies evolve. And actually, this is especially important because, let's say, most of the stars you can find in the universe exactly located in the galaxies like the Milky Way. So that's why understanding the Milky Way is quite important for galactic evolution in general. Again, a brief reminder. So the main stellar components which I'm going to talk about, the stellar disk, a thick and thin disk. I will discuss this. The bulge, it's also a part of, let's say, disk population. There is gas disk and the halo, which is made of stellar gas and dark matter material. And outline of my talk is pretty straightforward. I will be discussing the disk, the bulge, how actually the stellar populations from these two components interact, overlap, and interfere with each other, how these different components evolved and formed over time. So I'd like to start from the stellar halo. Let's close the disk and look at the halo delivered by Gaia. Looks quite boring, right? Smooth, faint, metal poor, nothing seems to be special. Of course, that's not true. Even before Gaia, we knew that there's lots of things going on in the halo of the Milky Way. There's a number of streams from disrupting dwarf galaxies. Let's say the biggest thing is the Sagittarius stream. There is Monoceros stream. There's different sort of overdensities. They're faint, but still they're visible. They were detected even before Gaia. But with the arrival of Gaia data, we started to reach, let's say, to hit the limits of the magnitude that we can detect. So currently about 100 new streams have been discovered using Gaia data. The fact that we observe these structures as streams, so like as coherent structures, suggests that these objects formed relatively recently. There was not much time then to mix and to be destroyed by tidal forces from the Milky Way and so on. Another example is here. So many streams from that we observe around the sun and the halo actually coming from globular clusters. And that's how actually the streams from all globular clusters may look like. You would be able to observe that. So far, we're still trying to reach this. Okay, so these are, let's say, small things, important details, which tell us about, let's say, recent events, ongoing processes. But what about the real elephant in the room, the real revolution by Gaia? So here I'm showing you the color magnitude diagram from Gaia Tier 2 for stars with high tangential velocity. So it means that there is no much disk contamination for these stars. And you can clearly see the presence of two sequences in the stellar halo. If I zoom in a little bit and draw a couple of isochrons, you will immediately see the presence of two populations. One is slightly metal rich, another is slightly metal poor compared to each other. These both populations are old, so it's like 10, 11, 12 giga-years old. So, and quite naturally using the kinematics or some other parameters. So the red sequence here is a thick disk, all part of thick disk. But what is the blue sequence? Once we looked at the chemical composition and more detailed orbital analysis. So here is a classic magnesium over iron versus metallicity plane, whereas this is well-known thick disk. But this blue population represents very low metallicity tail, typical for actually dwarf galaxies. So it's nothing else than a accreted star, right? And it's not surprisingly that we discovered this accreted population in the Milky Way halo, because that's the natural outcome of galaxy formation in cosmological context, right? So that's what we have in external galaxy and in simulation. So it was totally expected to find, right? And it's everywhere. So whatever combination of coordinates you take, you see the presence of so-called Gaia sausage Enceladus. So it was initially called Gaia sausage because it was discovered as a non-rotating population in the purely kinematic space. This is radial velocity, which is, let's say, in galactic coordinates, and this is rotational velocity. So see, it shows no rotation compared to thick disk. Similar diagram here, showing you something like a tumor diagram, which is very much different from rotating stellar populations in the disk of the Milky Way. And again, chemically defined, very distinct population. So the Gaia sausage Enceladus is the biggest event that happened in our galaxy some time ago. So how this merger may look like? Well, let's look at simulations. So in left, I'm showing you, let's say, the main galaxy, broad young Milky Way, and this is the infalling satellite like Gaia sausage or GSC. So you see the orbit together with population of globular clusters. So you can see that this disrupted dwarf galaxy, let's say the remnant of this merger covers, let's say, almost whole halo, the entire volume. So it's further away than, let's say, the in situ pre-existing stellar population. At the same time, in the volume that is available for us, these two populations, the in situ and accreted populations, they overlap a lot. Okay, brief overview of parameters that we know measured with some precision, parameters of the GSC. So it's really the biggest structure in the stellar halo. So its total mass about 10 to the 11, with stellar mass, well, some 10 to the 8. So it's like small or large Magellanic cloud. So it's really a big thing. So it was accreted about 10 to 11 gig years ago and hit a pre-existing disk. So the orbit of the merger, let's say parameters of gas that was accreted, effects on the star formation history, and some internal properties of this dwarf galaxy are not very well constrained. But we're working with it. So as I already mentioned, so the in situ, the pre-existing Milky Way stars and these accreted populations, they overlap spatially, right? But how we find a way to associate each star with two populations. Long time ago, even before the Gaia arrival, so it was suggested that so-called integrals of motions, for example, total energy or angular momentum, should be approximately conserved for the system, for a small system that's accreted onto a Milky Way. For example, if we start the simulated, let's say, so each color represents here a small accreted system. This is vertical coordinate of the angular momentum, but this is total energy. And after some time, so the special location in these coordinates for each this, let's say, accreted structure, they remain preserved. Isn't really the case for the Gaia sausage Enceladus merger debris? It appears that's not really, because it was quite massive. So here's just again an example from the simulation. So this is initial distribution of energy angular momentum. We see rotating disk. So this blue points correspond to globular clusters. This is accreted, the GSC populations. That's what we have in the end. So it turned out that if you have this relatively massive merger event, so these integrals of motions are not really conserved because there is a lot of dynamical friction. The galaxy is non-axisymmetric, so its mass is growing. So it all messed up things. You can see the huge overlap, first huge overlap in this kinematic space between accreted and the in situ. And also the globular clusters from these two populations tend to overlap. But we still can use the fact that the angle, these parameters, these kinematic parameters are not conserved, and essentially the merger debris is being spread out across this kinematic space. So let's look at a cosmological simulation. You may say, well, that was isolated. Let's look at cosmological simulation. So here are the different examples of different merger debris in a couple of cosmological simulations, which I will introduce in a minute. What I want to point out here is this radial structure of the progenitor. It appeared that if we color code this energy angular momentum space by the distance inside my dwarf galaxy before it was accreted, we can see this nice color ready. Why is this happening? So imagine that this is my satellite, my Gaia-Enceladus-like merger. It's been falling onto Milky Way, and that's what we have. So, and the reason for this gradual stripping of and the gradual distribution of my merger debris in the energy angular momentum space is the fact that, let's say, outer parts, let's say, they're less bound to the satellite than being stripped earlier. So they occupy this upper part of the histogram. So while the inner, let's say, the core of the satellite is sinking towards the very center, to the very deep of the potential well, so it propagates towards the lowest energies. So in other words, if we have an initial radial metallicity gradient inside my Gaia-Enceladus-like galaxy, then maybe there is a way to constrain it. Okay, yeah. So that's what simulations also predict. So they also predict this metallicity gradient as a function of total energy for individual merger debris. So you see different examples. So red is high metallicity, blue, dark blue is low metallicity. So it's very typical for Gaia sausage-like mergers. And it turned out that if we use the data from from APOGEE spectroscopic survey, and we managed to calculate the distribution, the distribution of possible gradients as a function of total energy of the merger of accreted stars representing the merger debris of Gaia-Enceladus. And it turned out that we found there, well, whatever value, because the units are quite bizarre, right? So it's dex per energy. And once we compare it with 10,000 simulations plus 10,000 tailored simulations plus cosmological simulations, it appears that in order to create the metallicity gradient of the merger debris we observe in the data, we need a metallicity gradient, the real dex per kiloparsec inside our GC progenitor in order of 1 minus 0.1 dex per kiloparsec, which is quite typical actually for the present day dwarf galaxy. Right, so it appears that at the time of the merger, already like 10 or 11 gig years ago, there was a metallicity gradient inside the dwarf galaxy. Quite remarkable. So as already mentioned, that the Gaia-Enceladus hit, it impacted the dynamics of stars in the disk. So it means for us that there was already the disk in the Milky Way at the time of the merger. And let's say when people discuss the properties of the Milky Way disk, one of the main, from the chemical point of view, characteristics is this distribution of alpha over iron versus metallicity, where people define two so-called high and low alpha sequence. And yeah, so here's another example. This is alpha over iron versus metallicity plane, but thanks to the progress in spectroscopic observations and analysis of the data, we also have ages. So we can, instead of showing this alpha abundance as a function of metallicity, we can show it as a function of age, right? So that's why this high alpha sequence was formed earlier and this low alpha sequence was formed later. And the Gaia-Enceladus merger hit about this time. So therefore, we expect to see the impact of this merger for stellar populations seen here, right? What kind of impacts we expect? So we expect some heating, right? So then people suggested, let's plot rotational velocity as a function of age for stars, let's say, close to solar radius. So that's why you expect to gradually decrease, let's say, of the mean rotational velocity with age. Like all the stars, they should rotate a bit slow. But this is for all stars. But if you select stars for the so-called high alpha sequence, that's what I get. You see, that's what we are looking for. See, I changed this color scale from linear to log, and it's quite. So you see that there was an impact, and it's visible in the kinematics of stars for all stars, but it's quite gentle. So that's why, if we want to understand, let's say, the properties of the disk, what's the, and in particular, this is APOGEE data. Well, this is, I will go to this, but this is mostly APOGEE. All right. Yeah. And obviously, since we have this merger exactly at the time of this transition from high to low alpha sequences, it was quite naturally to say, okay, there is a coincidence that the merger hit exactly at the time when this transition happened. Coincidence, or it's or there is a physical connection between these two events. Before going to the details of, let's say, impacts of mergers for formation of, or let's say, transition from high to low alpha sequences and creation of these bimodalities, some years ago we decided to look what kind of conditions we need to create to produce this sort of bimodal distribution of alpha elements, the function of metallicity. So we run several simulations. Let's say they're isolated formation of this from the cooling case. And it turned out that it's quite common to find, this is now theory, it's quite common to find these bimodal distributions in these purely isolated simulations, cooling gases case. But and these simulations actually produce quite remarkable agreement with the data. For example, in the inner part, we have this only low alpha sequence and the high alpha sequence when you go in the center. So these different plots correspond to different galactic radii and different heights from the midplane. So in the very center, we have, let's see, both populations. Once we go in the center, we go up. Okay, now it's okay. Awesome, thank you, sorry. Right, back, isolated simulations, bimodality. So what we learn from this simulation is that the physical conditions matter. So in particular, the high alpha sequence, this part, is formed during a short phase, during the intense star formation rate period, with a very high star formation efficiency, but depletion time about 1 giga-year, and at the time when the gas infall dominates. So it's like sort of non-equilibrium. So there's too much gas, so it's being accreted, and despite of high star formation rate, high feedback, there is not enough energy to stop this infall. So it's like non-equilibrium evolution. But over time, this process stabilizes, and we can reach sort of equilibrium infall outflow mode. Next, I would like to go to, okay, now let's look at what's going on in cosmological simulations. So here I'm presenting the Hestia simulation of the local group. Of the local group, and each simulation we produce a pair of galaxies, sort of Milky Way and Andromeda. So yeah, so this is zoom-in simulation in fully cosmological context, huge box, using constrained initial conditions. So in the way they designed to reproduce, let's say, the realistic local volume environment. So we have a pair of galaxies, which is nice. So we can start comparing not only the Milky Way data, but Milky Way and M31 versus the data. And what we had in this simulation is that here I analyze only 3 simulations, the highest resolution. In each we have a pair of galaxies. And we have 3 galaxies with bimodality, which looks, well, somewhat similar to what we have in the Milky Way. So we have these 2 sequences. So there are lots of panels, but maybe if you want to see it, this is distribution of alpha elements. You see clearly 2 distinct peaks. Well, 3 cases with no clear bimodality. And surprisingly or not, maybe it's just a coincidence, if we compare one simulation where we have in Andromeda and in the Milky Way, we have one bimodality in the Milky Way like galaxy and nothing similar in another case. And that's what current data show you. So there is, as I mentioned, bimodality in the Milky Way, but maybe not much in Andromeda. Maybe it's just a coincidence, maybe not. Okay, this is just few simulations. They're realistic in terms of environment, but let's go to larger scale. Let's look at TNG50 simulations. Here I'm using about 200 galaxies from TNG50 simulation from Anneliese Plepich. So I don't need to introduce this simulation. They're very well known here in Heidelberg. And here is just based on projection stellar density from this model. And here is the, let's say, magnesium over iron versus metallicity for each of the galaxies. I'm not inviting you to analyze each one in detail and find your favorite one. I did the analysis for you. So it turned out that, let's say, most of the galaxies show something like mono-sequence populations. About 13%, something really, really messy, not like the Milky Way. And about 1/3, surprisingly high fraction, shows something that looks reasonably well compared to the Milky Way. So let's see what's going on with these galaxies. So here I compare the average star formation histories for these three types of galaxies. So we see that, let's say, mono sequence population, they acquire the stellar mass slowly. So it's very slow cumulative star formation increase. While this complex, I call it, let's say, complex relation and alpha bimodality, they go quite similarly. But at some point, the galaxies with prominent alpha bimodality, they slow down the star formation. And if we compare this with the Milky Way, you might see a similar behavior for the Milky Way star formation history. But at the same time, the Milky Way looks quite extreme. Looks quite extreme if we compare with the average. But if I plot all star formation history shown here of 200 galaxies, color-coded by certain parameter, and on top you see in pink the Milky Way. It might be extreme, but not the upper limit. So at the same time, so it seems that the Milky Way is not extreme. There are many galaxies like the Milky Way. And if we know the properties of these galaxies, how they evolved, how they formed the disk, for example, it turned out that the Milky Way, so the galaxies in TNG, like the Milky Way, with bimodality, with similar star formation history, they form their disk very rapidly. So here you can see the moment when the Milky Way appeared to be disk dominated, so which happened about redshift 2.5. So it's not only the disk start to form, so it's already disk dominated galaxy. Okay, let's go back to the bimodality issue. So the idea we explore, I remind you, is that what's the impact of the last major merger or GSE-like merger? And what's interesting for us is these distributions. So this is the distribution of time of the last significant merger. It appears that for the blue, which is galaxies with alpha bimodality, the last major merger happened quite long time ago in a similar range, surprisingly similar range that we have for the Gaia-Enceladus. For other types, this, let's say, last merger, well, may happen anytime, essentially. So it means that not only the environment of galaxies, but also the evolution of environment matters. And maybe to demonstrate you what's going on, I'm showing you the evolution of one of the Hestia galaxies. You see the stellar content of let's say, the history of assembly of one of the galaxies of Milky Way-like galaxies. You see this chemical abundance relation. This is star formation history. And here's the number of galaxies, number of dwarf galaxies, which I can count inside the variable radius of my head. So you see, this is last major merger. So it's not that massive. Maybe it's not correctly to call it major mergers, but less significant merger. So it's mass ratio about 1 to 5, and mass of gas like 25%. So it's not a huge amount of gas. At the same time, so it hit the galaxy. Everything's fine. But as you can see, the star formation rate drops. But at the same time, the number of dwarf galaxies, number of mergers also decreases. So it means that this last major merger does not really produce this bimodality. It simply tells you when the environment in your galaxy you're living in changed. So, and in this way, last major merger, the most important word here is last. So it tells you when the merger-dominated epoch ended. So in the galaxy can continue in a more quiescent way. Okay, let's change the gear. So we discussed halo and the formation of some disk components. Let's discuss how we reconstruct the present day structure of the Milky Way. Despite the huge progress in Gaia observations and spectroscopic surveys, we don't observe the Milky Way like this, right? So these are external galaxies. But if we want, for example, to map the density of stars, we have the stellar density, that would look like this, exactly. So this is, here is the galactic center. We see a huge upper density around the sun. And if we care only about positions of stars, we would end up with like 10 to the 8 stars in our sample. If we want to do like dynamical analysis and to see how stars are moving, see the area shrinks, the number of stars decreases, let's say, by an order of magnitude. Of course, we want to do more. We want to have chemistry, and not only just chemistry, but precise. We want to have several abundance elements. So when you see how the volume where we have is decreased. Now, when I was looking at this, quality cuts when you do your analysis, no, we can do better, I believe. So in here where I'm going to show you some equations, just a few. So we know Milky Way quite well. We know the mass distribution, then we can write its gravitational potential as a superposition of several components. We know the contribution of stars, dark matter, maybe from gas. So we measure circular velocity of the Milky Way. We have star counts in the galactic center. So we know scale lengths and scale heights of stellar population. So with certain precision, we know the potentials of different components of the Milky Way galaxy. And of course, individually, we know if we know the potential, if we constrain the potential using whatever kinematic tracers, we have the density, 3D density distribution of stars. In 1979, Schwarzschild proposed the following idea, which is relatively simple, right? You have a distribution of stars, the density of your object, and you have orbits of your tracers. Then you can calculate weights for each orbit in your sample in a way that altogether, the superposition of these weighted orbits result in the desired density distribution. This Schwarzschild approach is being intensively used for extragalactic studies. But what about Milky Way? So in the Milky Way, as I already mentioned, we know with certain precision the total gravitational potential, 3D, non-axisymmetric. And we have 6-dimensional phase space Gaia or Gaia/APOGEE like data. And if we can find a way to calculate this weight, so we can maybe reconstruct the structure of our galaxy. Here I'm going to show you a little animation how this superposition orbiting works. I'm going to show you here how if orbits of all stars have equal weights, and here is already the solution for this equation. So at first it's going to be one by one, but then you see we start, obviously our sample is APOGEE, giant stars. You see how the density increases, the solar radius, and then every 1,000 orbits all stacked all together give you something like this. That's the density of stars in the APOGEE sample propagated using the orbit from the superposition. So it turned out that solution of this equation gives you very nicely the weight for the orbit. You might say, okay, you had this APOGEE input sample, then you get reconstruct density, but that's what you had initially. You already had this 3D density. The trick is, for example, if you want to map the chemical abundances, you can propagate your measurements about ages, metallicity, or other elements along the orbit. Then when you stack them together, weighted according to the weights from the Schwarzschild approach, from this mean metallicity map, you obtain this covered, the whole galaxy is covered using the observational data. So what you can do, as a byproduct, you are getting immediately the mass growth of the galaxy if we have ages, right? So here in gray is the age distribution of apogee stars in my sample. You see, so it increases, peaks around like 8 gigayears ago, and there is second peak. But then once I do the orbital superposition, that's the black line shows you the age distribution. But now it's already mass weighted. And I can decompose it. I can see the separately the distribution of ages or the mass growth for high and low alpha sequence. And it turned out that the high alpha populations is about 40% of stellar mass, while the rest is obviously low alpha. So what else is interesting? Obviously, the high alpha are oldest, so they're peaking around like 10 years ago, while low alpha, the stars are much younger. What else? We can correct the survey selection function. It's always quite problematic when you have the spectroscopic survey. You have few measurements, and you don't really know. Can you trust when you plot, for example, radial metallicity gradient? Can you trust your measurement? Is it complete information that with this superposition orbits you can correct for the selection function? So this is, let's say, raw input from the apogee data. You see that low alpha here dominates, let's say, low metallicity. But in fact, when you do this calculation, it turned out that, let's say, most of the mass here in low alpha should be, low alpha should be more metal rich. And here are how, let's say, these high and low alpha populations look like. So this is low, look like thinner component, and this is compact high alpha. But I want to mention, to underline. So chemically defined high alpha is not the geometric thick disk that we have in external galaxies, right? Because the thick disk in the outer part is made of low alpha populations that flare. But it turned out that the relative fraction of, say, high alpha and thick disk are roughly the same. So it's about 40% if you want. So the thick disk of the Milky Way seems to be 40% of the total stellar mass. Okay. It's time to look at the age metallicity relation, how the Milky Way galaxy evolved. So that's what we had for the apogee. You see this several clumps, not much. So lots of weight we had for young and low metallicity stars. But once we do this orbital weighting, we have this nice sequence that shows you actually, I can even highlight. So this is when, let's say, the low alpha part of this bimodality formed. So it's relatively recent. And I will show you where the stars are. So this is old high alpha population. And this third blob is metal-rich population, let's say, intermediate population. You might ask, what's the density structure of these different things? So the background map is the metallicities, magnesium over iron versus metallicity plane, and each panel shows you the radial distribution of so-called monoabundance populations from this particular point. So you see its exponential distribution for the entire high and low and high metallicity low alpha sequence. But this low metallicity low alpha sequence, it's like a broken exponential profile. So if you plot it, it would look like a ring, right, surrounding this inner metal rich low alpha part. Okay, what else it can do? We have these azimuthal metallicity variations caused by the bar. The nice thing is that we see that, so these lines show you along the bar major axis. So inside the bar region, the metallicity is high along the bar major axis, but surprisingly, the trend is inverse outside the bar. Okay, let's touch quickly radial migration. So that's one of the processes that shapes, let's say, the present-day structure of this. So it's a very well-known process where stars formed at a given radius, they're being scattered by spiral arms or something else, and they're being scattered across the disk. And in the end, for example, at solar radius, when you see where the stars coming from, they come from different radii. And let's say the observational manifestation of this is the change in the metallicity distribution function as a function of, for example, a different radii. It also affects the radial metallicity gradient. So that's what we also can clearly see. So this is high alpha sequence. It's very flat everywhere. But with age, you see the blue, there is that the metallicity, let's say steep metallicity gradient, which flattens with the stellar. Some years ago, we proposed a new mechanism for radial migration caused by the slowdown of the bar. So when the bar forms, it's naturally slowing down because of the dynamical friction with the dark matter haze. So that's why the rotational velocity of the bar decreases over time. And at the same time, the location of resonances, the main resonance of the bar, they're moving outwards. And therefore, the stars that captured by the resonances, they can be captured in the inner galaxy. They're being moved away. And the stars, if they're captured in the center, they were metal rich. So that was, let's say, the way to bring supersolar metal rich stars to the solar radius. Here is an example of the orbits of these stars. You see, for example, here, star being captured by the bar resonance is being moved outward. And what we have in the data. So recently we used this idea to understand the metallicity gradient as a function of radius for stars of different age. It appears that, for example, here I'm showing again the APOGEE sample. For all stars, there is this break in the radial metallicity profile. So which shows you where the stars, the metal-rich stars, they were transferred to, let's say, more or less solar radius, and then it stopped. But you see this kind of effect only for all stars, for stars that they of age like 8 to 10 gigayears old. And the same process we see in the Milky Way, in simulated galaxies. So which tells you, so at the time when stars formed, the metal-rich stars formed in the very center, and the very first episode of the bar formation. So it's quite intense in terms of radial migration. So it brought some metal-rich stars to the solar radius. So that's why we constrain the epoch of the bar formation of about 8 to 9 gigayears old. So I think because of some technical issues, I need to skip some of my slides, quite unfortunately. I'm happy to discuss, for example, the Milky Way bulge reconstruction. So with orbital superposition method, we can just scan the density in 3D. And we can see this abundance trend. So you can see that this is mean metallicity map. You see very metal-rich diskish part, then this pop-up region because of the presence of the X-shaped, so-called X-shaped structure. So it's a natural process that regulates the formation of the Milky Way like bulges, so-called buckling instability, when you form a bar initially in a very thin configuration. And at some point, because of the too very high radial velocity dispersion, it starts to buckle. So it's like something like close to fire hose instability. And this actually results, so let's say the result of this buckling instability is different depending on the kinematics of stars. Let's say for cold, as you can see, here's an example where we have simulation with cold disk and hot disk. So and for cold stars, you see more prominently, more detailed structure. And that's actually what we can observe in the Milky Way, right? So this is, again, the reconstructed galaxy, and this is the density distribution for different populations along the metallicity. You see that low metallicity stars, they show more or less something like close to spherical distribution. But once you go to the high metallicity stars, they show more prominently, more sharply density distribution. So this is orbital reconstructed. So this is APOGEE data. Yeah. So we also have kinematics. At the time where we're exploring this sort of Milky Way bulge formation scenarios, there was another Gaia discovery, which was very famous phase-space spiral. And when I think about our power buckling models, it appears that when we have this vertical bend, we observe the vertical waves passing, propagating from the inner galaxy to the outer. And as the result. That's what we have. So in, let's say, in this scenario, when the vertical waves created by the bar buckling, we call it buckling echo model, and a remarkable agreement with the Gaia. Of course, I cannot avoid mentioning other scenarios where the Sagittarius galaxy causes something similar, and long-lived halo perturbation can be also prominent. And in the last chapter, couple of minutes, I'm going to mention the spiral structure up from Gaia. So when the Gaia Tier 2 arrived, we obviously were super excited, and we see, okay, we want to see spiral structure. That's what we get in the density, right? We see many stars observed at the solar rate, at solar vicinity, but yeah, not much further away. So you cannot really trace the density variation caused by the spiral arms. And the reason, actually, two reasons. First, the shape of the, let's say, Gaia footprint, the number of stars observed in different directions, and also affected by the extinction. But at the same, so it's like, it's a technical issue. At the same time, there is also physical, it's oscillations of stars around their guiding radius, right? So once the star is moving along the orbit, so it oscillates around some median radius. So we decided to, say, tackle these two problems. First, we can randomly sample the Gaia distribution. So we just randomly select the stars to make it flat. And the second, to avoid this impact of radial oscillations of stars, we can convert, let's say, this physical x, y, z coordinates to pseudo-guiding coordinates, simply replacing galactocentric distance by the guiding radius calculated using angular momentum. Work quickly. Yes, so this is just to illustrate how this works. Sorry, can I speed up? So this is your physical x, y, and this is guiding. So you start to see things more sharply. And yeah, that's what we get. From here, and using these pseudo coordinates, we got these over densities. Of course, it's not a physical space, it's just a pseudo space over density. Then if we select stars in these over densities and map their location, we can actually match. It turned out that the stars in these over densities, they match the location of spiral arms traced using maser measurements and something else. At the same time, we found that some of these over densities correspond to the bar, the resonances of the bar. So from this, we estimated the pattern speed of the bar, about 38 to 41 kilometers per second. Yep, so this is, I think, my last, almost last slide. So using different spectroscopic data, we also found that there are systematic metallicity variations along the spiral arms. So it turned out that, let's say, the stars inside these over densities, they're more metal rich. There are several mechanisms proposed for that. So currently, I don't see the way, let's say, to disentangle. A nice thing, maybe not a nice, but the surprising thing is that this, let's say, enhancement of metallicities has seen also perpendicular to the deep midline, which was quite surprising and not fully understood. And here's my summary. So we're really living in the golden era of galactic research. So thanks to Gaia and many other surveys, so the unknown, uncharted territory is shrinking. So what we are facing in a couple of years is just this arrival of more data from spectroscopic surveys like Milky Way mapper from SDSS-5, foremost moons, BEEP. So there will be, galactic astronomers will be busy. So at the same time, in order to understand, let's say, to interpret this observational data, the community is hardly working on the improvement of models, cosmological and daylight. So the studies of Milky Way, they're really, really interesting, and they're now already useful for understanding external galaxies, but I believe in a couple of years with all this data and theory, so we will be able to learn more. Thank you.
Thanks, Sergey. A lot of super exciting results. I guess the floor is open for questions, and I would encourage first the students to ask questions either on site or online. So please. All right. We have.
Thanks for the great talk. I was curious about your results with the bar-induced radial migration. So do you have a sense of how significant this efficiency with the bar-induced radial migration versus just spiral arms, like what we expected from like the original kind of mechanism of radial migration? How significant difference would there be in efficiency?
So in my view, thanks for, yeah, that's a really deep question. So in my view, spiral arms, if they are the major source, they work constantly. There is no way if you have a, let's say, gas rich or let's say gas thumping galaxy, you should have spiral arms. It's transient, most likely. Okay, so that's why you expect, let's say, the radial migration. Let's say spiral arms cause radial migration, not depending on the function of phase. At least you should see the gradual increase, let's say, in your metallicity distribution, or let's say certain skewness. So there should not be sharp change in the, let's say, metallicity profile as a function of age. That's not the case, perhaps, for this bar scenario that we see in the simulation. So we see that at certain age, your radial metallicity profile just changes significantly. And this age corresponds to the time of formation of the bar. So
I think an important difference is that the bar pushes only outwards, whereas spirals scatter you in and out. And at the corrotation radius and at the OLR, the spirals heat you up as well, but can do either way as well. And the bar only does outwards and heats you up as well. So it's a little bit different what happens.
At the same time, spiral arms normally rotate slower than the bar, so their resonance is.
Yeah, but you could. It depends whether you're inside out, where you are on your horseshoe orbit, and it's broken. So it's more a diffusive process with the spirals, but bar it's not a diffusive process. It pushes you always outwards.
Once in a lifetime, hopefully, maybe.
Also a question, but maybe. Several question effect. I mean, we are also looking at this TNG simulations because of course everybody does, but we found that unfortunately the implementation of AGN feedback is such that at a certain time when the central black hole reaches a certain mass, essentially all the gas is removed from simulation very efficiently, very quickly, which is unrealistic because you'd expect that it would not remove the cold gas in the entire disk. And so we found that alters the dynamics quite a bit because the cold gas is important for the dynamics. And of course, in the simulation, the cold gas is not resolved, really. I mean, so that's why it's not cold, right? So that's why it's removed. And you should see this. I mean, this should have an effect on the enrichment and everything. So it must be problematic. Did you look at the resolution effects and these sort of things?
So we didn't look at the resolution effects, so it's just statistically. Regarding the gas fraction, we have in the paper where we studied the bar formation in the TNG and compared it to the Milky Way, what we noticed is that the effect that perhaps you're talking about, this gas removal, we did not associate this with the AGN, but we see that, let's say, the gas is being removed in the galaxies with bars. So, and therefore, if there is an impact of the bars on the AGN, on, let's say, the black hole feeding, then there might some physical meaning in that, right? So if you're from bar, you have gas inflow, then you, let's say, remove gas.
But the gas is removed. The gas is moved out to several kiloparsecs, right? So it's because the AGN feedback essentially becomes all of a sudden very efficient, and the simulations don't really resolve the gas. So the cold gas is not. I mean, in real world, the cold gas is not blown away, right? All the energy goes out vertically, more or less, right? And so that's unrealistic, and that means that the following simulation evolution, the gas dynamics is different than it should have been. And that is surely a resolution effect. And I was wondering whether you have, that should also affect the metallicity evolution here. And so I mean, we also found, by the way, that the bar slowdown is quite different. It's not always like this. Some bars actually don't slow down at all, and some slow down, go even faster.
At the same time, there are some
all sorts of things happen.
The Milky Way bar is slowing down nowadays.
Currently, yes.
Currently, yes. yeah, perhaps it's really worth also to let's say to plugging the AGN evolution or the black holes evolution in this story. I agree. Thank you.
More questions?
Thank you for this very nice talk. So there's a lot of information, so I need some time to process. But I have a question about the distribution of stars coming from like GAC, like a collision event. I think you showed a figure in the first part. I think, showing distribution of stars in the kinematic space. Yeah, something like this. So I would imagine that GAC like galaxies would come with like satellites. Can you say anything about the orbit or like, the debris from such satellite of GAC like galaxies?
So okay, may I rephrase your question? Can we say something about the orbits of accreting satellites by looking at the, for example, energetic momentum distribution? Is it correct?
Yeah, kind of like, what if these galaxies, these accreted galaxies have satellites? How would they look like in the space of like kinematics?
When we look, let's say, in cosmological simulations, what we see, let's say, the most of galaxies being accreted, at least with prograde orbits, so which makes things worse, right? Because they're more overlapping with in situ. So just like there are just a couple of examples per galaxy where you have retrograde. At the same time, even if you have a prograde merger, you always have, for example, I think like this, you always have this tail, this retrograde tail. So it's massive. For massive galaxies, it's always massive. So that's why I'm a bit, and again, it's also, you can see that there are lots of different substructures being formed in a single event, which again, kind of
so you
adds
don't think
to the dispute about the existence, let's say the reality of different substructures. I believe that we should start thinking how we maybe not discover new evidence, but start to linking them together. That, I believe, would be the way to progress in order to understand the assembly history of Milky Way using GALAH.
I mean, I guess that's why we measure chemical abundance of stars. Yeah.
Maybe I have a very naive question. You mentioned with Gaia DR2 and DR3, we had this elephant in the room called GC. And I was wondering with Gaia DR4, 5, and moons foremost and stuff, do we have the chance to find another elephant, or it's going to be like smaller scale elephant?
So elephant was found in DR2. The DR3 didn't find, I wouldn't say anything, but no major substructures were surprisingly found, despite, let's say, the increase by factor 5, 7 in number of stars with 6D information. So it perhaps, since we're sitting at solar radius and we still cannot penetrate the very innermost region of the Milky Way, I don't expect any big discoveries unless we're going to use infrared mission, infrared surveys. I believe maybe SDSS, Milky Way mapper, moons will help a lot. And also that's what simulation suggests. Let's say the early mergers, they should sit in the very center, and they should be relatively compact. So that's why we see only the latest merger, which we luckily can capture at solar radius. So that.
Then let's wait and see. Let's find out. Last opportunity for a question. One last minute question. No. Well, first we should thank again Sergey for a very nice talk. And we're gonna slowly move towards the Altstadt to Hemingway's for some dinner. So if you're interested in joining us, just follow us right now. And for the people online, we're minutes. And one final announcement. Next week, we're gonna have Yamila Miguel from Leiden Observatory. She will tell us about peering inside giants, how solar system information and JWST data transforms our understanding of exoplanet interiors. So stay tuned. See you next week. Thank you.